Here's the second part of a couple of ways to graph quadratic formulas, or sorry, quadratic functions and parabolas. Last time we looked at tables of values and using the vertex axis of symmetry and a couple of points on either side of the vertex to graph. And this time we're going to look at using the axis of the vertex and both intercepts, the x and the y intercepts, as points to create a graph. So not too different from the last time, except that we're going to pick the y-intercept and the x-intercept to create some values. So starting off the same, we're going to find the axis of symmetry and then the vertex. Then we'll look at some factoring to find the x-intercepts. We'll put it in intercept form, and then we'll plug in zeros for the x's and find the y-intercepts. So the last step actually is really easy, and I don't have to do it last, but I'm just choosing to do it last. So looking for the axis of symmetry means I need to identify A, B, and C from my function. A is the quadratic or the squaring terms coefficient, it's 1. B is the linear coefficient, it's -10, and C is the constant, 21. The axis of symmetry has an equation whose form is x equals the opposite of b over 2 times a. So substituting in the values from the function, x equals the opposite of -10 over 2 times 1. -10 is +10, divided by 2 is 5, so the axis of symmetry's equation is x equals 5. I'm going to use that to find the vertex. I use the value x equals 5 and to find the y value of the vertex by plugging it into the original formula. So I'm plugging it into y equals x squared minus 10x plus 21. So y equals 5 squared minus 10 times 5 plus 21. And simplifying that, 5 squared is 25. 10 times 5 is 50, so 25 minus 50 is a -25. -25 plus 21 is a -4. So the y coordinate is -4, and the vertex is 5, -4. So now I found the axis of symmetry, I found the vertex. Now I'm going to find the x-intercepts, and to find the x-intercepts, I want to put this into intercept form, which means I need to factor. So what's happening when you're finding x-intercepts is you're setting the whole equation equal to 0, and if I did that, right, so oops, didn't mean to erase that, x-intercepts. So I'm setting that whole equation equal to 0, or y is equal to 0, x squared minus 10x plus 21, which means I'm going to factor. We're going to put this into x-intercept or intercept form. So 0 equals, and I'm looking for things that multiply to give me 21 and add or subtract to give me -10. Let's do that over here. 21's factors are 1 and 21. 2 doesn't go in, but 3 does. 3 times 7. Nope. 4, not 5, not 6. I think we're done. If I choose 3 and 7, and I make them both negative, when I multiply, they'll give me a +21, and when I add, they'll give me a -10. So I'm going to factor x squared minus 10x plus 21 into x minus 3 times x minus 7. Then it's in x-intercept form, and it's very easy to see where those intercepts are. They are at x equals 3, and x equals 7. And if I want to write them as points, it's going to be 3, 0, and 7, 0. So let's plug all of that into a table. The table going over here. So here's x, and here's y. I've got my vertex, 5, negative 4, and I've got two x-intercepts, 3, 0, and 7, 0. Let's find a y-intercept. So to find the y-intercept, I want x to be equal to 0. So that means I'm going to plug in 0 wherever there's an x. So 0 squared minus 10 times 0 plus 21. I'm just plugging 0 in for x, which leaves us with y being equal to 21. So when x is 0, y is 21. Now we really have enough information to get a pretty good sketch. So the vertex is at 5, negative 4. 1, 2, 3, 4, 5. 1, 2, 3, 4. And the two intercepts are at 3, 0, 1, 2, 3. And 7, 0, 5, 6, 7, 0. And the y-intercept is at 0, 21. So let's see, here's 5, 10, 15, 21. And then I'm just going to make a little sketch. And I have a pretty good idea about what that graph looks like. If I wanted more points, I could put in more points. But I know that this is a graph that's opening up, and I have a sense about where the roots are. And if I needed an initial or a starting value, my y-intercept, I'd have that too. The last method we're going to look at is putting the equation into vertex form and then using transformation rules. So vertex form, you'll remember, is y equals a times x minus h squared plus k. And we love this form because we can use all the transformation rules to figure out where the heck the parent function has been moved to just by looking at the equation. We're going to need to complete the square. So we're going to use completing the square. And if you haven't watched the completing the square video yet, don't worry about it. Just kind of hang in there and follow along. And eventually you're going to learn about completing the square. And you can come back and take another look at what's happening in the vertex form. So if it's seems a little confusing, the method for completing the square right now, hang in there. It's going to get better, and there's going to be a video specifically for completing the square. We're also going to be doing an activity when we meet on Thursday that will help you understand completing the square. All right, so we want to get it into this form, but right now it looks like this. 2x squared plus 4x minus 1. All right, I'm going to set this equal to 0 because I want to move some things around. The completing the square process wants me to get rid of the a term first. So I'm going to divide everything through by 2. This by 2, and this by 2, and this by 2. Of course, the 0 gets divided by 2, which doesn't do us too much good, or at least doesn't change things. That just stays as a 0. 2x squared, however, becomes x squared. 4x becomes 2x, and negative 1 becomes negative 1/2. Now I'm going to move the constant terms over to the left. So I've got to the right. So I've got x squared plus 2x equals 1/2. And I'm going to do the magic number stuff with the linear terms coefficient. So remember, you divide the linear term by 2 and square it. 2 divided by 2 is 1. 1 squared is 1. And that's what I add to both sides of my equation. So x squared plus 2x plus 1 equals 1/2 plus 1. Now I've got a perfect squared trinomial, really easy to factor over on the left. X squared plus 2x plus 1, when it's factored, becomes x plus 1 squared. And remember, the magic number that we created ends up being the number inside the parentheses, so you can always just jump right to that step. Over on the right-hand side, I've got 1/2 plus 1, which is just 3/2. We're really close now. I want to clear the fraction, so I'll multiply both sides by 2. 2x plus 1 squared. And 3/2 times 2, or 2 over 1, becomes 2 times x plus 1 squared. On the left, and the 2's cancel, and I have a 3 on the right. And the last step, 2 times x plus 1 squared, subtract the 3, set it equal to 0, and there it is. It's been turned into vertex form. So h of x is equal to 2 times x squared plus 1, x plus 1 squared minus 3. So there it is in vertex form. That part's done. And once again, if you're freaking out because you have never learned about completing the square before, it's okay. There's a video on the way to learn how to do that. Right now, the next part should be easy. So if I handed you this form, h of x equals 2 times x plus 1 squared minus 3, you should be okay with telling me what the transformations were. How did the parent graph get moved? Well, one thing that happened was that it was moved to the left, 1. Another thing that happened was that it was moved down, 3. A third thing that happened was that it was stretched vertically by a factor of 2. So that means that it's going to be a little bit more closed up. Let's make a quick sketch. So the vertex is now at -1, -3. And it's going to be a little bit more closed. And there's our sketch.